Vincent from the American University in DC. I had actually the pleasure of meeting Michael. I had heard, of course, of Michael prior, but I had the pleasure of meeting him actually at his university last fall, and I was very, enthused and very nice meeting him. He is an electrical engineer by training, as a BS electrical engineering. Then he had the good sense of switching to something more useful, like mathematics, or the other way around, of course. But at any rate, Michael did his PhD in applied mathematics at Cornell, and he's done a lot of work in topological, computational topology in general, topological signal processing, and he's also worked on radar, and he did a lot of very interesting work with Robert Grice from UPenn, and it's a pleasure to have him here to talk to us about some of these topological concepts in engineering problems. He actually builds, and I'm ashamed to say I'm an electrical engineer, I don't build things anymore. He actually builds things in his basement to teach PDEs in his department. So it's a real pleasure to have you. The floor is yours.
All right, thank you, Hamid. That was a very nice introduction. And I didn't bring any of these things that I built, unfortunately. I'm sorry. The thing that I'm working on most recently probably would get me in trouble with TSA anyway. So yeah, what I want to tell you about is about sheaf theory. And the idea is that this is sort of a sales pitch, if you will, in that sheaf theory is the right way to handle a lot of signals in the world and gives you a lot of useful tools to get handles on understanding them in a qualitative but precise way. And so what I want to do is to give you a few vignettes of how sheaf theory might be useful in solving certain kinds of problems. So of course, as is obligatory, let me thank the people that I work with. So Robert Grice and his team at Penn. We have some industry consultants as well as a friend of ours, Yasu Hiroka, who's at Kyushu University. Of course, thank the sponsors, and there's a website address where you can read some preprints and all that good stuff. I'll put that up at the end as well. So honestly, my impression is that some of the best engineering problems out there, the biggest engineering problems, actually under the surface are about math. If you really can't solve an engineering problem, it's probably because there's a neat little math puzzle in there, which means you ought to learn the math and ought to use those mathematical techniques, or develop some new math to address them. So just sort of give you a little bit of flavor of the sort of things when Hamid says I build things. Well, here's a computer built out of discrete logic parts. It was a fun project at one point. But the whole idea of trying to solve the problem of computation led to the development of the theory of computer science and the theory of computation. Some really good mathematics. A lot of people have been working in computer-aided design. Curves and surfaces led to Bezier curves and things like that, which actually are really handy for solving differential equations. Of course, the fast Fourier transform, we wouldn't be talking all over the world easily without that, and more computing. And, well, any idea what this might be? Well, this here is actually a sonar image. It's a sonar image formed, it's actually a wall-penetrating sonar. That is the inside of my washing machine. And I was banging on the side of my washing machine and used an image formation technique, relatively standard back projection, to look at the inside. And you can see this is actually one of the wall beams that's supporting the side of that washing machine. And of course, GPS is very handy and requires a lot of mathematical techniques, including differential geometry, in order to correct for the relativistic effects. So I'm going to tell you a little bit about some ideas in signal processing, which is perhaps where I'm most comfortable. And by signal processing, I really do mean, honest to goodness, image formation, cameras, radars, communication systems. And so I want to sort of be motivated by these very realistic problems. Yet on the other hand, look at some of the mathematics in a way that perhaps you haven't thought of before. So there's a lot out there. There's a lot of people doing this kind of work. And essentially what I'd like to do is suggest that a lot of these people working on problems are actually have a common theme. And that common theme is about locality of data. Data being stored or being measured locally. And it has an impact. It has an impact on how you handle the problem. See, if I want to measure the temperature in this room, well, what am I going to do? Well, I'll reach for my parts bin and grab out a temperature sensor. Pretty much all the temperature sensors out there measure the temperature in the room, well, right here. Temperature might be different over here and might be different somewhere else in the room. All of these are local measurements. Same thing with pressure, same thing with electric current. Voltage is perhaps not quite so local, but it's along the same lines. It's actually sort of dual to that. And even if a phenomenon isn't local, usually when you take a measurement of, it is. Say, for instance, sound propagation. Wave propagation is not local, because obviously if it were local, I would be producing sound and you would not be hearing it. I hope you're hearing it, and if not, we can adjust the AV. But the point is this: your measurement of that sound pressure is local to you. The sound that you hear is slightly different than the sound that you hear. You're making local measurements of this non-local phenomenon. That's how we do remote sensing. And sort of a general observation, this is not a criticism by any means, but it's sort of an observation that pretty much everyone who's doing some kind of engineering measurement of a local phenomenon uses their own sort of framework, perhaps their own pet framework that says this works really well. Say in remote sensing, we use a particular set of techniques that are sort of tailored to radar or sonar or what have you. And people measuring temperature and pressure, they have a different phenomenon if they want to find out what's the temperature in the room. As a mathematician, this is a little uncomfortable. There ought to be a good unified way to handle all of these local measurements. Now, as a mathematician with an agenda, I think it might be sheaf theory. Now, I realize that this is sort of going out on a limb because I realize most people, including even most mathematicians, are sort of averse to sheaf theory because it gets really nastily technical. But I want to show you 3 examples where sheaf theory might be useful. So the first one is actually to talk about trackers, Kalman filters and related. Tracking is a problem that's been around for a long time and was developed in the radar community to track things. Although, of course, you can think of those same kind of tracking ideas for tracking a package on its way to your house once you've ordered it. And the problem with tracking a package from wherever you bought it, say wherever Amazon's warehouse, at least that's what happens at my household, is we buy something at Amazon, and somehow or another it gets to our house. And there's a path it takes, but we don't have a really, really good idea of where exactly it was. We don't have GPS coordinates on this package the whole way through, in much the same, sort of in contrast to the way that we would have it if we were a radar system tracking an aircraft. So how do you put those 2 tracking problems on the same framework? We're getting some kind of local measurements. The aircraft being tracked by the radar sees a local measurement local to the radar that says, all right, I think the airplane's over there. And then a little later, it's over there. Same kind of thing happens with a package. Someone scans the box on its way to my house at a particular spot. So is there a good way to put those together? And the answer is yes. There's a sheaf theoretic way to do this. Now, on the other hand, some of you have heard this sort of idea that electric circuits that compute logic, the sort of things that underlie how your computer works, these too have information stored locally, local to specific points on the circuit. Say if you're in the realm of CMOS, you're measuring certain kinds of currents to tell you about logic state. And what that suggests, since current measuring is a local phenomenon, that there's a good way to sheafify this problem. It's a fun word. Actually,
can I quote you?
You can quote me. In fact, Rob Grice usually extends it when he talks about this, and he says something to the effect of, I just make sure that the word sheafification shows up in my talk, because I like to say the word. But in any event, the point of the matter is this. This local information is there for the taking. Now, what you do when you design this logic circuit is you ensure that it has certain global properties. That given a certain set of inputs, I abstract away what happens in between. And there's a bunch of outputs that happen. And I want those outputs and to depend on those inputs in a particular fashion. And perhaps there's feedback so that it can store information. And so there are mechanisms to encode this sort of information in a sheaf. Now, why would I want to do that? People design logic systems very well, right? We all have computers and whatnot. They seem to work. Well, there's a reason for why you might want to do that, and that's, well, gosh, a lot of these systems require synchronous design. They require a clock, and that clock consumes a lot of power, throws off a lot of EMI. Throwing off a lot of EMI is sort of a deal breaker for packing a really heavy-duty, powerful processor into a cell phone. It obstructs your bandwidth. That's kind of bad. So it would be nice if we could get rid of the clock, but then you have to sort of face some other problems, and we'll talk a little bit about that. And the final example is actually one that seems like a toy problem, is studying transmission lines, but it's a really good model of dense urban environments, radio environments. So if you have a dense city, well, where do the radio waves travel? If you're sitting on or standing on the ground near a building, well, they're going to travel, for the most part, along the roads. That ends up looking something like a transmission line network. It's not exactly, but it looks something like, at least asymptotically to first order it is. And that, too, can be encoded. The measurements of the signal level that you're transmitting can be encoded in a sheaf. And when you extract some global information from that sheaf, it can tell you something about the kind of building network or collection of buildings that there are, and that might be obstructing your system. So it has some implications for mapping, sort of radiometric mapping of your environment, which is really important when you want to design these systems. So I'm going to use these three separate examples to try to suggest to you that really what they all have in common is a structural analysis. You want a theory that will tell you about local measurements that infers global behavior from the local behavior. Essentially what you want to do is say, well, I know something here. I've got some measurements over here. I've got some other measurements over here. And they're somehow consistently telling me a more global picture. Now, this catchphrase, global from local, was actually the thing that I took away in grad school when I was learning sheaf theory from the pure mathematicians there at Cornell. And they said, well, the way you do that is some machine called sheaf cohomology. I'll sort of show you what this can do for you in an engineering context. Now, the other thing that we tend to do is we tend to build systems by adding other pieces. If I have a logic system, well, I break out my soldering iron and I add more. Or if I'm in an urban environment, well, people tend to be building lots of buildings or removing buildings. Or if I'm in a tracking situation, maybe there's other additional things I'm trying to track. So when I add new information or new constraints to the problem, it changes the problem. It changes the local behavior and it changes the resultant global behavior. There's something called the Meyer-Vietoris exact sequence that modulates that and controls that. And that's the Meyer-Vietoris exact sequence for sheaves. And what would be really nice, too, is this local data might be of different types. Say, for instance, I'm tracking this package. And one kind of data that I might get is simply, it's here at this particular location. I might also get, it's here at this time. Or it's here at this time and was scanned by this person. So I get different kinds of data that I might have here that might be relevant, might not be. And that kind of information may change. So the question is, how do I put these heterogeneous local measurements together in a consistent global picture? The problem with a lot of the piecemeal approaches for doing some kind of synthesis is that they don't play well with different kinds of data. If there's different data types, you have to get very ad hoc about how you stick them together. My suggestion is that sheaf theory might be able to give you a way to do that by categorifying appropriately. Now, this last little piece is the most speculative of them, in that I can show you at least what the structure looks like, but I have a lot of trouble actually doing inference on that anyway. But these two, I have some definite examples, which I'll show you that show how this works. So, of course, if I'm going to be a mathematician, I'm going to tell you what the definition of a sheaf is. A sheaf is on a topological space is whatever. Sheaves assign local data to open sets. And the reason for sort of putting this over top of all the mathematical definition is the following. The mathematical definition is a particular formalization of this catchphrase. This catchphrase is the thing you want to be thinking of. And indeed, there are other variants of encoding, formalizing this idea of local data. And that's what I want to advocate. So what is a sheaf? Well, as I said, it's a way to assign data, local data, to a space. So here's empty space, for instance. And let's say I want to lay down some data that I've gotten. let's do a geometric example because it's really easy to see what's happening there. So let me stick on some map data, for instance. Maybe the data that I have corresponds to an image sitting over some portion, but I can't see the whole image. I can't see the whole thing. Say if you're on Google Maps, I'm only going to be looking at a little teeny piece on my screen. Or maybe this has been gathered from some remote sensor, as this one was, for instance. It lays down a particular sensor footprint and doesn't see anything else. So let's lay down some footprint here. And let's be abstract about it in that we're not requiring it to be a particular shape or size. We're just saying we're going to lay down a footprint. Now, of course, the thing that you want to do is you want to add some other data to help you understand that. Say, for instance, I'm going to lay down a road network or some other markings here. These might be target detections, for instance. This is all simulated target detections of targets moving around on this road, for instance. And one of the things that I hope you can notice, it might be a little difficult to see from the back here, the resolution isn't quite what I wanted it to be, is that, well, gosh, some of these detections here are not where the map is. And some of the road is not where the map is. And sometimes, like right over here, there's map but no road. So the different kinds of heterogeneous data can be laid down pretty much however you like. This sort of suggests that what a sheaf is it's a way to store this local data that can vary in type and quantity and possibly even quality, although that's speculative, as you move around in this space. Now, if you're a mathematician, you say, OK, good, that's what a sheaf is. If you're an engineer, probably the right thing to think of next is, well, how would I put this into a computer? How would I use this? Because this is not something that is obvious. So what you want to do is you want to think of the fact that, well, reality is local. At least that's a physical truth. Relativity, the whole idea of relativity is that reality is local. How closely we want to adhere to that particular mindset, we'll step back a moment from. But reality is, in some sense, local. So if you have the stage on which reality plays, this configuration space, we've got lots of measurements of various sorts. Maybe we have some signal strength measurements. Maybe we have some type and locations. All of this is sort of the real world. But I want to approximate this in some sense and capture the salient features in some kind of engineering system. The reason for this, of course, is on one hand, computational feasibility. There's no way I'm going to stick reality in my computer. Just not going to happen. It's even a logical paradox to try to stick all of reality, or even all of reality, the part that I care about, into my computer. And furthermore, I can't conceivably collect all of that information anyway. I'm not going to have enough sensors of enough types to pull all of that information anyhow. So that's not the right way to think about it. The right way to think about it is to approximate and boil down the space to a simpler space, and approximate the phenomenological models down to simpler things. For instance, the phenomenological model of radio propagation can be, to a large extent, approximated by wave equations. The idea of where am I, or what is this thing? This is a particular kind of vehicle. Well, you can boil it down to a bunch of features that are relevant to the problem you're interested in. The idea of sheaf theory is you build up the general framework that can handle any of these things and can use them for inference. Now, you realize I am somewhat of a mathematician, and I am a sheaf theorist and algebraic topologist. So I have to put a commutative diagram somewhere in the talk. And here's where our commutative diagram is, that our actual model of sort of the place where reality plays, it's got some data sitting over it. If we accurately represented that data, I should be able to go take a look at this data and get the same answer if I try to label it and turn it into features as I should if I come around and approximate the whole thing. So what this is suggesting to me is that this is a condition for accurately understanding when my approximation makes good sense. So now let me show you how to approximate the base space and what you should do with them. In particular, the idea of a sheaf as a thing over a topological space with open sets. Open sets are really nasty to work with from a computational point of view. Much better if we can work on cellular spaces. Much better if we can work on simplicial complexes, for instance. So I'll show you how to do that. It's interesting, historical note, a guy by the name of Alan Shepard, working with Bob McPherson, reasonably famous mathematician, then at Brown, in 1985, put together a PhD thesis where he studied sheaves over spaces like this. And in particular studied the derived category, for those of you who know what that means. And interestingly enough, after that thesis, Shepard left mathematics. And the ideas lay dormant for a long, long time. Sufficiently long that when we started our project doing some applied sheaf theory, trying to understand how we might manipulate local data a few years ago at Penn, we didn't really know what to do. We were kind of building up these pieces little bits at a time. But finally we got enough, and we were sort of excited enough that we showed these ideas to Bob McPherson. And he said, oh, you know what? I had a student a long time ago. You should read his thesis. It's worth noting that Yasu Hiroka, who I credited at the beginning of this talk, managed to get a hold of the copy of this, scanned the whole thing, and gave it to us, and we read it, and realized that this was brilliant. This was a good way to manage sheaves in a combinatorial way. And this is what I want to present to you as the right way to store sheaf theoretic and local data in pretty much any kind of engineering system. So let's start off with this cell complex. It's got a bunch of vertices, it's got a bunch of edges, and it's got a 2-cell. Of course, you can imagine your favorite complex, whatever it happens to be. But this one here is a certainly good one. Oops, let me back up here a moment. Why is this going? It's going the wrong way. There we go. OK, so what you do with a sheaf is you ascribe to each cell, you put a set of whatever, if you like, allowable labelings are permitted. So for instance, let's say this 2-face could be labeled with a 0 or a 1. Let's say this vertex can be labeled with 1, 2, or 4, etc. So label every cell in your diagram with a set. You can think of these as allowable values that can be placed in isolation to each one of these cells. Essentially what we're going to want to do is then we're going to want to make these consistent in some fashion. So I need to give you some kind of consistency relationships that say that, well, if I've made this labeling here of 1 here, there's only a certain number of possibilities I could pick out of this guy on an adjacent edge. This will encode some kind of consistency. So it turns out the right way to do this is to build from low-dimensional cells up. If you go from high-dimensional cells down, you get something that's analogous to a co-sheaf. But co-sheaves are not what I want to talk about at the present moment. So say, for instance, let's focus our attention on this vertex here. The allowable labelings I'm going to put on it are 0, 1, or 2, just for this example. And then what I do is to each one-dimension up face, say this edge, or this edge, I have a function that takes my set here to my set here. So for instance, if I have got a 0 here, the allowable labeling that must be on this edge is a 0 here. And say, for instance, what this particular says is 1 will have to map to 3 and 2 will have to map to 1. And I've got one of these for everything. Now I haven't shown them all. There's a lot of these maps for every particular set of pairs of edges that are, or pairs of cells that are in face relation to one another. Say, this guy here, actually, there's a map from here over this vertex to this edge to this face. Similarly, there's another path that goes from this vertex over to this edge to this face. I haven't shown that one. And being mathematicians, we want this all to be consistent. We want every possible combination in this diagram to give me the same answer. If there are multiple paths to get me from this vertex to this face, if I go this way, so go from here to here to here, it's the same as going from here to here to here. If you do that, you build up that data structure, that is a sheaf. And I think that the point is this. I can store this combinatorial information a lot more easily. Now, what does it do for me? I said there are possible labelings in isolation. Now let's see what happens when I try to label them all at once. So for instance, here's a labeling that's consistent with all of these various maps. So out of that set, I picked a 0 for this vertex. Well, that 0 has to map to a 0 for this edge and maps to a 0 for that face there. Similarly, this 0 had to map to a 1 on this edge and to a 2 on this edge. And perhaps I'd go a little farther, or perhaps I don't. Any such labeling that's consistent on some portion of this space is called a section. If it labels the whole thing, we call it a global section. Otherwise, it's a local section. Now, sections are sort of interesting in that there's usually a lot of them. Say, for instance, here's a different one. I've just relabeled some of these other cells. I've labeled this edge and this face and this edge, but I've not labeled this guy. And I can ask, can I extend this section from the set that I've just pointed to? Can I extend it to put a consistent labeling here? So think about it a moment and see what would I have to put where that question mark is. Well, there's actually a problem. There's actually a problem that one of the labelings, say this labeling of a 1 here, says if I look to the pre-image, it's got to be a 2. Okay? But if I look to the pre-image over here, well, let's see, what does it got to be? It is a 1 here. It's got to be a 2. That one's good. What about here? It's a 0. What's the pre-image? 1. Uh-oh. I don't have a consistent way to label this face. So this particular section that I had drawn does not extend. This is inconsistent local information. So what a sheaf does for you is it encapsulates that kind of consistency relation. And then it's sort of the business of putting together those sheaves that lets you do inference. Now, this is sort of awkward if you have to ad hoc dig through this sort of thing. It would be nice if there's a good way to enumerate all of these things computationally. And this is where the mechanism of cohomology comes in. The mechanism of sheaf cohomology is a way to extract this global information from a sheaf, the local information. Now, I'm not going to write down the definition of cohomology here. It's not terribly involved, but it really doesn't quite fit on the slide nicely. And furthermore, essentially what I want you to think of is it is a machine. It is a functor, which is to say that if there is some local structure in the way a sheaf is put together, then it preserves that local structure. Essentially, if I have two sheaves here and I have a map between one of them to the other, I have a way to transform this local data into this other local data, then that gets preserved on the level of cohomology as well. So it doesn't screw up that kind of local structure, or that kind of sheaf theoretic structure. So it's very handy. Now, what it does for you, among other things, is it tells you all of those global sections. It tells you every last one of them. And it gives you a nice, this is an algorithmic thing. The idea, of course, is that it's going to look a bit like homology, but it's got homology where the cells are labeled by elements in the sheaf. And when you do your standard kernel mod image game, you end up with everything fitting together, and you end up with similar kinds of invariants, with the arrows going the opposite way of homology. Okay, so what this does for you is the analog of connected components, for instance, H0 is actually all of the global sections. But you get other things. You get other kinds of invariants that essentially amount to obstructions to doing the extension. That section that I showed you a moment ago that said I can't extend it to that vertex, that gets recorded in some of the other homology classes. And there is a homology class corresponding to that failure to extend. So the nice thing is, it's got all that information. Even better, there is a nice way to take cohomology over parts and glue it together and understand how to stick it together using a Meyer-Vietoris exact sequence, essentially much like in standard homology. So now let me show you some examples, show you how this works. So the first thing I'm going to tell you about is network flows, which I'm thinking of as a generalization of tracking. And the idea goes something kind of like this. Suppose I've got a collection of targets or packages moving along on a particular time path. Say, for instance, these are three packages from Amazon and 2 packages from LL Bean, for instance, moving along, and they're on their way to various places. Well, they come into a distribution center, and one of them goes this way, and 4 of them go that way, etc. Well, what you should imagine, if everyone's distribution network is operating reasonably efficiently, the number of packages coming in to each distribution center, it better be the number going out. Maybe this doesn't always happen, and sometimes you have the package that gets lost. Maybe that, I don't know. But the point of the matter is that sort of conservation rule suggests that I ought to think about labeling the edges of this distribution graph, this distribution directed graph, with some kind of data that says I've got A packages here, B of them here, C of them here, D of them here, and they have to satisfy a rule that says something like A plus B equals C plus D. Similarly, at this other vertex, it's a vertex of in degree 2, out degree 1, maybe it should say D plus E is equal to F, just in terms of tracking total number of packages. Say you want to keep track of the identities of packages, you could stack up some direct product of this structure where I've got keeping track of each of the different kinds. Although that's, I think even that's a little too simple. I think we could do more. But let's just keep it simple for the moment. So you can store it in this kind of information, store all of this information in a sheaf. In particular, if you want to keep track of numbers of targets, probably you'd start off by keeping track of it in the integers, although there's a little bit of a defect with the integers. Negative packages doesn't make a whole lot of sense. So the right mathematical object to keep track of that is a semi-ring. Best example of a semi-ring, of course, is the natural numbers. And perhaps there are other semi-rings out there that you're interested in working with. You want partial semi-rings that say that, well, I'm going to max out. I'm not going to have a capacity too large. In any event, what you do is you store over each edge the number of packages in transit along that route. And over each vertex, you keep track of the in degrees and out degrees of each of those various packages in motion. That data structure looks something like this. So here's sort of the spatial representation. Here's the data structure representation. Here's an edge, another edge, another edge, another edge. And those maps telling me about consistency are going to link up that degree 4 vertex with each of its various connected edges, with projection maps being the arrows. Similarly, over here, we've got something doing the same thing for this vertex. And how do we encode the fact that there's a conservation law? Well, we don't take the whole direct sum here. We take some subset along which that conservation law is satisfied. So this gives you a sheaf theoretic model for tracking targets, or for tracking packages. I keep saying targets because the last people I showed this to were DoD. Now, you can have this local consistency problem that says, well, you know, I sent in 3 packages and 2 packages into this distribution center, and 1 came out and 4 came out. But that's not consistent with the fact that here 8 packages came out and only 3 went in. So probably 3 went along, or probably 5 went along here. So there's some kind of inconsistency. Someone lost track of that package. And the fact that I can't label it this way, this is not a legal section. In particular, I cannot extend the section labeled in black to this red edge, indicates that there's a problem. So by using that element of cohomology to tell me that's there is a useful inference. Now, what you'd like to do is go ahead and try to actually build up an inferential framework for this, where the following kinds of things can happen. Say, depending on if you know what's going on the black edges, I've got a good handle on what those distribution routes are, you can reverse engineer what's happening on the others for the most part. So the one we were just looking at says, well, I've got the wrong number of targets. I had 5 coming in, and there should be 4 on this edge, and this one says there should be 5. There's no way to say that data is compatible. It's inconsistent. On the other hand, here, this is the first picture that I've drawn. This here has to be 4. And here, I don't have enough information. So there are many possible inferences to tell you what the track is, what the various packages are doing along these tracks. So the interesting thing is that you can take this idea, you can take this methodology and build up a sheaf. Now that I've shown you the sheaf of all the data, you can build up a smaller sheaf that has just the data you measured. There is an exact sequence that links those guys up for which there's an inferred term that tells you something about ambiguity, tells you about how many different possible inferences you can make. When you look at those possible inferences, you say, well, you know, what does this feel like? This feels very much like sampling theory. I've got this object that I'm pulling out little pieces of. Is this really sampling theory in disguise? Short answer is actually yes. You can use this framework to prove the traditional Nyquist theorem. You can sit down and write out a model of a band-limited signal, and you can say, I'm going to sample that band-limited signal on some sub-graph of my space, and ask, what does the sheaf cohomology tell me? What does this exact sequence tell me? Well, it turns out precisely when it says those vanish, those terms vanish, those obstructions vanish, is exactly when you've hit Nyquist. So that's sort of interesting. And I'm going to leave that there for a moment and show you a few other vignettes. So logic circuits are another example that I posited that is a good place to think about local data and inferences. Of course, the framework of logic circuits is that I've got some kind of wired up thing. And yes, for me, that really means I went and bought a bunch of logic chips and probably soldered them together and was trying to figure out why the heck the thing wasn't doing what I wanted it to do. I want a tool that will let me dig into this without having to simulate the heck out of the thing. Because, well, for one thing, okay, I'm an academic with not a whole lot of financial resources, so I don't want to buy the expensive circuit design software. On the other hand, I'm lazy. I don't want to wait a long time if I don't have to. Some of these simulation tools take a long time to run. So I want some way that I can quickly get a qualitative but precise view on the matter. And I think sheaf theory gives you that to some extent when you're building asynchronous circuitry. So essentially what you do is you take your logic circuit and you boil it down to a connection graph. That first NAND gate there has got 2 inputs and 1 output. And really from a topological point of view, that's really all there is to it. This NAND gate here has got 3 inputs and 1 output, and it's connected to the first one by a wire. And so that all of that connection information is, of course, encoded here in this directed graph. But now, of course, what did I lose? I lost the logic. So let me put that logic back in by showing you what information I might want to store. Well, these are ideally binary circuits. They take values 0 and 1 on each of the wires anyway, because the wires are the thing I can measure. If I've got the circuit sitting on my bench, I can't measure the inside of this thing so easily. I'm not going to grind the top off of the chip and stick little probes. I'm not going to do that. I'm just going to take a look at the wires. And I'm going to infer that there's probably some internal state being tracked at each of the logic chips. OK, but this tells me the information I need to tell you about these ways to manipulate and check consistency. Well, here's what it does. Here's what you do. Say you take projections going back. You say, well, I'm just going to keep track of the inputs here and project over 1 to there and 1 to there. Now, what do I do going the other way? Well, that's where I do the logic evaluation. So, for instance, this was a NAND gate initially, so let me take the NAND of these two things to generate the data sitting over that edge. So what this object does, and of course I haven't outlined all of the various possible consistency relations you've got, and consistency functions I have on this circuit. You do this over the whole thing, and you have now a sheaf structure. Turns out this is not what you want. Sort of obvious thing fails in a big bad way, because in particular, in order to make that cohomology operate, there's one little technical point, and this stopped me for a while, is that cohomology requires all sorts of linearity and niceness, because mathematicians think the world is linear, and when it's not, they kind of get worried. Well, logic circuits are kind of not linear. Kind of not linear in a whole bunch of different ways. For one thing, they're not linear in if I take a NAND gate and I take the NAND of 0 and 0, I get 1. Doesn't sound very linear to me. So I better do something about that. And eventually I realized that the way around this problem was to really put the mathematician hat on and own it. And say, well, the way we dealt with square root of -1 was to define it to say, well, it's square root of -1, and we're going to use it. So I'm going to do the same kind of thing here. I'm going to categorify my logic. I'm going to say each one of these various kinds of states, the logic 0 or the logic 1, really I'm going to build up a whole vector space where one basis element is logic 0 and the other basis element is logic 1. I'm going to let myself take linear combinations of logic 0 and logic 1, which has some interesting consequences. For one thing, a 0, 0, say, that says it's not logic 0, it's not logic 1. I don't know what it is. Or it's logic 1 and it's logic 0 at the same time. What's that? Oh, well, that means that it's doing something. It's changing. It's a transition. And the neat, nice thing, this is a general categorical fact, is that if you do this to any kind of set or function on sets, they automatically lift to linear functions. So you can do this pretty much whenever you have the data that sort of fails to work. And so automatically what you get out the other end is a nice way to sort of understand time-changing circuitry. Not really time training as in this is the sequence of events it did, but rather I can tell if things are in transition or not properly defined. So I can go ahead and build up a sheaf, which I've tentatively called a switching sheaf, kind of going along the lines of switching theory, that essentially says what I'm going to have to do is I'm going to have to take all that data over this vertex and work now in this categorified setting. Sadly, when I take a direct sum and I categorify it, I get a tensor product. So it gets computationally a little harder to work with, but it's not too bad. You could do these computations actually by hand. I've computed a number of cohomology in switching sheaves by hand. My students have done it too, and they haven't died. And furthermore, to make everyone's life easier, it's easy enough to code into MATLAB. Not that one wants to do integer valued computations in MATLAB, but never mind that, I'm lazy. Okay, so let me show you how this might work. So here's a circuit. This is a sort of infamous circuit. This is a glitch generator. It's supposed to always have logic 0 as the output, regardless of what the input is. But if I switch that logic on the input, it should still be 0, except for the fact that there's a potential time delay in here. And that can cause you to get a little glitch on the output. And let's see if we can detect that. So let's turn it into a connection graph, and let's label it. Let's label each of the vertices. This one here has got one input, and so we take the tensor product of this two-dimensional vector space, a logic 0 spanned with a logic 1. That's still one-dimensional. Over here, what happens? Well, when I restrict going back, it's essentially just a lift of a projection. So it's an identity map there. And here, going forward, we're implementing the inverter. The way to look at this is to see those two matrices and realize that this one's kind of going this way and this one's kind of going that way. It's inverting. It's switching the logic 0 column with the logic 1 column. Similarly, over here, what am I keeping track of? I'm keeping track of the inputs to this, and I'm taking the tensor products of all the logic 0s and 1s. Looks like I'm building a K-map. I am. And indeed, here's the K-map sort of encoded. It duplicates information a little bit. That's all right. And so this ends up being a linear matrix now, way to manipulate what's going on. So let me sort of cut to the chase and show you what it does. Here's that little glitch. Let me switch. If I switch A up or down, well, if I switch up, there's no problem. Going from logic 0 to logic 1, the output stays at logic 0. But when I switch from logic 1 to logic 0, I get a little bit of a glitch, whose width is that width of that propagation delay. OK, well, here's the two usual states. This one here, what I've done is I've computed for you. Turn the crank on cohomology. This is logic 1 as input, and the output is logic 0. Here's logic 1 as input, and the output is still 0. And there's this additional thing. The H upper 0, the global sections of this sheaf, instead of being generated by the 2 we expected, has some additional state. There's a third dimension. This one here, notice, is saying that I have a logic 1 and a logic 0 superposed on the input, and the output has got a logic 0 and 1 superposed on the output. I am in transition. It is possible to make this circuit do something interesting. Interestingly enough, we don't know exactly what it is doing. It could be going from 0 to 1 or 1 to 0, which is saying that we've lost some information here. I don't know that it is the falling edge of the input that's the problem. But I do know one of these edges is the problem. And a good way to detect that is to say that there's a particular section, a particular local section that's been obstructed. There is a race condition. And you can tell that by the fact that there's another element of cohomology that has showed up. You can do the same kind of thing with memory elements. Memory elements are really handy. This is the sort of thing that I remember terrorizing ECE 101 students. Build this logic circuit, say, what is it doing? Well, if you write out the truth table, there's a whole bunch of inconsistent states. Those inconsistent states show up. Those inconsistent states show up as elements of the one-dimensional cohomology, which is an indication that there's trouble. In fact, these are the usual nice set, reset, hold states. But then there's additional transition states that tell you that it exits that hold state in an unstable way if you try to set and reset at the same time. And finally, let me tell you a little bit about transmission lines. Some people call these things quantum graphs because physicists like things that have the word quantum in the front, as far as I can tell. Essentially what you do is you build up a graph. Take a graph and you label it with energy, waves coming in of a particular frequency. Yeah?
So, can I take you back to a few slides?
Sure.
About the race condition various.
Yeah.
So I'm trying to put together some of the things you said. So we said before that the cohomology tells us about the number of global sheaves.
The zero cohomology tells you all of the global sections. Yes.
So when you say tells us, is that how? I mean, what is the relation between number of global sections and
okay, so the dimension of that cohomology is the number of global sections. Actually, the dimension of it is the global sections form a vector space, right, and that is the dimension of that space of global sections. So in this particular case here, I have a three-dimensional space of global sections, and I have illustrated for you a potential basis for it. I've written it out on a potential basis.
And so what does the first cohomology give us?
So these particular elements, when you go ahead and do some interpretation on them, take a look at what do they seem to correspond to. What that tells you is a logic 1 here on input, and the other one is a logic 0 on input, and they're being held stable. Now there's this additional guy here is when it is when you enforce it to be in transition. That is what this global section basis element tells you. Now of course you can take linear combinations of these, but then they're in Z2 coefficients. You don't really find too much else. So I think the question you're asking there is a really sensible one, which is, well, this isn't exactly the information we would have necessarily expected to find here. Why is it, and what is the right interpretation to this? And in particular, it looks like we've lost information. Did we lose that information by abelianization, or did we lose that information because we did something stupid? I don't know the answer to that question yet. That's an area that I'm trying to understand.
The local restrictions we put, are those the boundary operators here?
Those essentially end up being the boundary operators, yes. Yep. Okay. All right. So I see just a few more minutes, so let me sort of hit the high points on this. Essentially the idea of...
This is also kind of the same, or at least the rejoin is also kind of the incidence matrix.
Yes. What typically you show up here with is something that looks like an incidence matrix. It's not exactly the standard incidence matrix, but it's the same kind of information encoded in there. Absolutely. So what you do with a quantum graph, as various people like to call it, essentially you're asking, what is the solution to the wave equation restricted to this graph? What does wave propagation look like on this graph? Well, you end up with traveling waves on each of the edges, and at vertices, you have some kind of energy conservation conditions. So you can encode that by saying, at each vertex, I know the incoming traveling wave amplitudes, complex numbers, magnitude, and phase. So here at this vertex of degree 3, I have 3 incoming waves. And when I restrict my attention down to a particular edge, there are 2 traveling waves, one going to the left and one going to the right. And conservation of energy tells you how you ought to take the incoming waves and turn them into incoming waves incident to this vertex into waves moving around on this edge. Now, one of them is really easy. The incoming wave to this vertex is one of the traveling waves. So that's this row here. What about the other one? That other one comes about from a little bit of analysis that says, I want to have actual energy. And you sit down and write out the physics to say, conserve energy there. And you end up with that particular row that shows up. So you can go through, and the neat thing is that I can take this graph and simplify it, collapse it along a spanning tree. Each one of these collapses turns out to be an isomorphism on cohomology. So what this is saying I can actually study all the waves moving on this graph rather than this big complicated thing, instead on this rather simple thing, a bouquet of circles with a bunch of extra tails. And then systematically, if I'm interested in, say, this portion of the graph, I can work my way back and uncollapse, essentially pull back my information and study that graph at whatever level of detail I want. So what's kind of neat is you can use this idea to actually reverse engineer the geometry of the graph. Essentially, you can, not remote sensing, but rather local sensing, figure out what the geometry of this graph is just by looking at its sheaf cohomology at various frequencies. And as a neat sort of side benefit, it's possible to image the entire graph on a much, much smaller set of frequencies than was previously thought. If you sit down and ask the physicists, they have to do something spectral, which usually involves big operators with lots of spectrum. This methodology here lets you do it with very, very few frequencies. So what's next? Well, for one thing, I'm really interested in understanding some engineering problems where there's some local data that you don't have the foggiest idea how to manage that data. The data management problem is a really big problem. And sheaves, if nothing else, are a data structure that's really easy to manipulate and really nicely handles that information. Lets you do inference on it. And what I'd like to do is understand how to put together all of these problems into this common framework that lets you do inference reasonably, in a reasonable controlled fashion. So that's really where I'm aiming with this whole idea, and why I've presented several very different examples to show you that sheaf theory was really a useful organizing principle. So thank you for your time, and I'll happily entertain any questions.
Any questions? Adam, any questions?
Yeah.
I've asked this to a few kind of mathematician sheaf theory people and not necessarily gotten a consistent response, but if you don't know anything about sheaf theory and you wanted to learn,
Right.
I know it's kind of, there's a large barrier to entry.
There's a massive barrier to entry. And it's one that we're trying to actually solve right now. I put up Justin Curry's name as one of the people on the Penn team a long time ago. He's actually writing an introductory sheaf theory text. And I'm actually also doing the same thing. So hopefully within the next year or so, there will be an easy way to get you into the theory. In the meantime, my suggestion is this. Do not start with Kashiwara and Shapiro, for instance. That is a book that is very, very difficult. Braden's book is how I started. So Glenn Braden, B-R-E-D-O-N. That's not a bad book to read. It's fairly technical, but it's not too bad in terms of reading of that sort of material. Of course, Shepard's thesis is actually extremely readable. A problem is it's hard to get a hold of. And in fact, we've been told specifically from Brown University that they want anyone reading that thesis to go through them, which is especially difficult to circulate it. But that said, that's really the quickest way to get moving. I can't get around that sort of copyright nonsense. But I'm sorry it's not the most satisfactory answer.
So in terms of computations, though, I mean,
yes.
You're saying that you're just using basically MATLAB?
I'm just using MATLAB, which honestly, one of the major lessons learned from the applied and computational topology community is that you need to do reductions first. Because otherwise, you put any reasonable sized problem on, you're going to get into trouble. Unfortunately, all of the reductions out there rely on essentially a sheaf of constants over the region where you're manipulating. That has implications to how we can do computation. And at this point, we don't really know what the right way to proceed there is. For my own part, I think the right way to proceed from an engineering point of view is to use Meyer-Vitoris. Split the problem up into little pieces, do the computations in a distributed way, and merge them together. But that's more of a principle than it is an actual, I've coded it up and it works kind of answer. So sadly, I don't have the ability to say, well, my MATLAB code works on everything. I know my MATLAB code works on small problems. I know that for small problems, I can do similar sorts of things in Python and not really end up beating myself up over it.
Any other questions?
I have a question.
Yes.
Sure.
Because I'm from a very different discipline.
Mm-hmm.
I'm an electrical power engineer.
Yeah.
So my question is, when you are doing this network reduction, as you show later in
Yep.
your presentation, how much information can be preserved actually? Do you actually lose any information by collapse from like a 5-node system to a 4? And then
Okay. So theorem, in that particular context, you don't lose any. It's an isomorphism. Now, it's an isomorphism on cohomology. It's actually even a little better. It's actually an isomorphism of sheaves. So in fact, when I do that particular collapse in the case of quantum graphs, I lose no information. Essentially, what I have to do, though, is I have to collapse on a spanning tree. If I collapse a loop, then I do lose information.
Yeah, because in our studies, if you want to collapse one system, you actually use the equivalent system to replace it, but some topology information will be lost. So if you are getting from a lower system to a
Right.
reproduce it from a lower degree system to a higher
Right.
one, then you actually cannot unless you preserve that information in some other format.
Sure. Essentially, what you might want to think of it in is this way. When the collapses on that particular sheaf, the reason why they're in isomorphism is very specific to that problem. Now, if you were to step back and say, more generally, what do I get when I collapse? What you get is a morphism of sheaves, which that morphism of sheaves tells you how to translate the information that can be preserved. Now, the problem is, if I did lose some information going from here to here during that collapse, that's sort of a problem. But from a mathematical, analytical point of view, it also tells you what information has to be put back here. And you can imagine a sequence of these reductions collapsing, say, one particular portion at a time. What that means for us is that that particular mathematical object has a special name. That's a resolution of sheaves. That resolution of sheaves tells me what how to organize the information, and in particular, at which portions is the information critical. So in particular, if you're interested in solving local problems, then you can look in that resolution of sheaves, and it will tell you, if you're interested in this local problem or this sort of half local problem, you need this information, this particular portion of information, and nothing else. And so you can work with a somewhat reduced network. But it's not the sort of thing that gives you perfect reconstruction unless you're very careful and are in the right setting.
In other words, usually the reason we lose information is because we normally just store a quantity like voltage or,
Sure.
or current. So this is more like the physical variables,
Yes.
attributes for the network. But
Yes.
we don't store in the same way the topology information,
Right.
like the nodes or the connectivity and things like that is not stored. So you're saying in this sheaf structure, it actually stores different type of information in that specific.
Yes. Yes. In fact, it encodes some topological information up to, depends on exactly the sheaf. In good situations, it stores up to homotopy type, which is essentially capturing how various loops in the network are, how many are there, and roughly how they're connected together.
So isn't this a database?
It is essentially a database, yes. A sheaf can be very nicely thought of and reasonably accurately thought of as instructing you what kind of database is necessary to store your information.
Okay, yeah, I think that's easier for me to perceive because I think that will be, for example, this node.
Mhm.
You will have a database actually can store different type of variables.
Yes.
Like my voltage, current, my nodes, and then where I locate is even the GPS information on that for that the specific nodes.
Mhm.
So you probably just use a matrix of that can actually host different variables.
Yes,
Just
and
put everything in it.
some of that is topological information is what it's keeping track of. And the nice thing about sheaf theory is that it forces your hand into making certain decisions about what kind of information you're going to store, and then it tells you what the penalties are for not storing that.
Thank you.
Yeah.
If you have a distributed sensor system where you don't have as many sensors as you would like, so typically you would estimate
Right.
a particular point,
Mhm.
do these sheaves take the place of the estimation algorithm, or do you feed the estimated data points into the...
Okay, so what the sheaves do is they, rather than saying they do the estimation for you, what they do is they let you know, they perhaps give you a certificate that says I either do or don't have to estimate. And to sort of to fit your idea, if I have a sensor network, you can imagine putting in where I've got enough data to represent the whole thing. That's sort of a theoretical object. And if the network is working properly, it boils that information down to some smaller piece that is missing some of the data that I'd like to have. typically that forms, and that was that commutative diagram I drew, if that really happens, if that really works, if that is a good representation of my data, then I will end up with another sheaf whose cohomology characterizes what information I've lost. In particular, I'm missing these sensors and it didn't matter. Or I'm missing these sensors and it does matter. And if you look at that cohomology, it will tell you whether or not that's important or not. And that fits along the lines of what I was saying with the Nyquist theorem. You can write out this sort of, imagine a network of sensors that's just on a line. I've got some measurements of a signal that's band limited sitting over them. And I ask, which of these samples do I need in order to recover the signal? If I don't have this one, what is the effect on that signal? What is the effect of my reconstruction? At best, what can I do?
So, since you can determine which data points you do or do not need to estimate, you can save yourself a lot of computational time.
Potentially, yes. Potentially. I mean, Hamid's point is really important, which is, well, okay, computational, just how hard is it? Yeah. And that's computational sheaf theory and cohomology theories are not where computational homology theories are. I mean, computational homology has done very well over the past 10 years. Sheaf theory is just sort of getting its start now.
Time to get into it if you want to make an impact.
Absolutely. Join in.
All right, let's thank our speaker again.
Thank you.